we begin our lecture on Module 3 on Eigenvalues and Eigenvectors. Finding Eigenvalues and Eigenvectors. In finding eigenvalues and eigenvectors, we consider the equation that is the determinant of lambda sub I minus A equal to 0, which is the characteristic equation of the matrix A. Moreover, when expanded to polynomial form, the polynomial, which will come from the determinant of lambda I minus A, will be equivalent to lambda raised to n plus c sub n minus 1 times lambda raised to n minus 1 plus ... until we have c sub 2 times lambda square plus c sub 1 times lambda plus c naught, which is actually the characteristic polynomial of A. So the eigenvalues of the square matrix A correspond to the roots of the characteristic polynomial of A. So what we're actually doing here is to simply solve for lambda, which are actually roots of the characteristic polynomial, or the roots of the characteristic equation if we have the lambda I minus A to be equivalent to 0. So these are the steps in finding eigenvalues and eigenvector. We let A to be a square matrix as an n by n matrix. First, we form the characteristic equation that is the determinant of lambda I minus A to be equal to 0. It will be a polynomial equation of degree n in the variable lambda. Next is to find the real roots of the characteristic equation, and these are the eigenvalues of A. So for each eigenvalue lambda, we find the eigenvectors corresponding to lambda sub I by solving the homogeneous system that is the lambda I minus A times x equal to 0. Now this can require some row reducing operations on a square matrix. The reduced row echelon form must have at least one row of zeros. So for example, in example number 5, we're asked to find the eigenvalues and eigenvectors of A. So here we will have A, which is a 3 by 3 matrix. Find the eigenvalue and corresponding eigenvector. What is the dimension of the eigenspace of each eigenvalue? So to begin, again, we start by coming up with the determinant of lambda times I minus A and setting that one to be equal to 0. Okay, so if you like, instead of multiplying lambda to an identity matrix, which is a 3 by 3, and subtracting from it your matrix A, what you can do is you simply consider all the diagonal entries in your matrix A, and for each diagonal entry, you simply have the lambda minus. So for example here, we can have lambda minus 2, lambda minus 2, and lambda minus 2. And then just solve for the determinant of this matrix by a cofactor expansion. But since this matrix that are given to us is a triangular matrix, we know that the determinant of a triangular matrix is simply the product of the diagonal entries. So hence, the determinant of lambda I minus A in this case is simply lambda minus 2 times lambda minus 2 times lambda minus 2, or that will be the cube of lambda minus 2. So the characteristic equation is now the cube of lambda minus 2 equal to 0, for which we get the root lambda to be equal to 2. So to find the eigenvectors of lambda equal to 2, we can now form the homogeneous linear system that is represented by lambda I minus A times x equal to 0. Now since lambda is here equal to 2, we substitute the value of lambda in this expression. So we ended up, say, with 2 minus 2, 2 minus 2, and 2 minus 2 here. This will be the resulting matrix. So we will have a matrix wherein we ended up with 2 zero rows, and this implies that x sub 2 is just equal to 0, and we can consider say x sub 1 x sub 1 and x sub 3 to be our free variables, and using the parameters s and t to represent x sub 1 and x sub 3, we can conclude that the eigenvectors of lambda equals 2 are of the form. So we will have the eigenvector x with the corresponding components x sub 1, x sub 2, x sub 3 is equal to, so since we will have x sub 1 to be s, and then we know that x sub 2 is 0, and then x sub 3 is equal to t, which resolves into two vectors. Say we will have s times the vector 1, 0, 0 plus t times the vector 0, 0, 1, wherein s and t not both 0. Lambda equals 2, therefore has two linearly independent eigenvectors. So we can see that each vector are unique and cannot form each other. So the dimension of its eigenspace is equivalent to 2. In theorem 7.3, this tells us about the eigenvalue of a triangular matrix. So if A is a square, if A is an n by n triangular matrix, then its eigenvalues are the entries on its main diagonal. So for example, we're given two matrices here. For A, we will have a 3 by 3 lower triangular matrix, and in letter B, we're given a diagonal 5 by 5 square. That's a square matrix. So obviously, since we will have a triangular and a diagonal matrices, the eigenvalues of each matrix are simply the entries in its main diagonal. So in A, the eigenvalues are 2, 1, and negative 3. And in B, the eigenvalues are negative 1, 2, 0, negative 4, and 3. Okay, so now without using the theorem 7.3, that is, if we do not know that, we do not have any knowledge about the theorem that for a triangular matrix, the eigenvalues are the entries in the main diagonal, we can try to check or find the eigenvalues for a triangular matrix using the concept on that is the determinant of lambda I minus a equal to 0, which allows us to solve for the eigenvalue. So doing that, again, we consider the diagonal entries, that is 2, 1, and negative 3, and we simply come up with lambda minus 2, lambda minus 1, and lambda minus 3. So we have it here, lambda minus 2, okay, sorry for that, lambda minus 2, lambda minus 1, and lambda plus 3. And let's say using a cofactor expansion, we don't need that, no? Because we ended up, since this is still a triangular matrix, okay, we can see that we will have the entries in the main diagonal as lambda minus 2, lambda minus 1, and lambda plus 3. So since the determinant is the product of the diagonal entries, we will have lambda minus 2 times lambda minus 1 times lambda plus 3, and equating it to 0 by applying the zero product property rule. Then we can solve for each lambda. So say lambda minus 2 is equal to 0. So lambda is equal to 2, and again lambda minus 1 equal to 0, so that will be lambda equals 1, and lambda plus 3 equal to 0, you have lambda is equal to negative 3, which are the main diagonal entries of A. Now in B, okay, applying the same concept, we can see that the entries in the main diagonal are the eigenvalues of the matrix. So we will have negative 1, 2, 0, negative 1, 2, 0, negative 4, and 3. So that will be all for today. So again, we can see that we can solve for the eigenvalues of a given matrix by simply applying the determinant of lambda I minus a equal to 0, which gives us a characteristic equation wherein the roots of the characteristic equation lambda are the eigenvalues of the given matrix. Also, we can verify that an eigenvector is the eigenvector of a given matrix that is associated to a lambda by simply applying AX is equivalent to lambda X.